Hi, everyone. We'll be starting in just a minute or two. All right. Yes, I'll try. Okay. All right, so shall we get started here? Let me stop my share here. And you see me twice. You see me over my shoulder. That's not very good. Here, maybe we can adjust this. There we go. That looks a little bit better, right? A little less creepy. All right. Well, welcome everybody to CC Colloquium for whatever the date is, October 20th, 2021. And I'm actually the host this week, so it's my great pleasure in just a minute to introduce our guest. Before that, are there any announcements from anybody in the crowd or anybody online? I know there's no announcements from CC leadership.
Open house for Friday evening with the grad students.
All right, open house Friday evening for the grad students. Is there anything more that they need to know about that, or do those
6 to 8, and I'll be sending another email reminder with the link to come in and see us.
Okay, great. So with that, unless there's any other announcements, it's my great pleasure to introduce Kim Lau, who, as I mentioned, she didn't see this, so now I'll embarrass her, that she is an up-and-coming rising star in geosciences, paleoenvironmental research. And so it's really, really great to have her here. Sorry that she couldn't be here in person. She's sorry too, but pandemic is still what it is. So a little bit about Kim. So she got her bachelor's at Yale. Oops, I should keep this out of my camera range, huh? She got her bachelor's at Yale University in 2009. She went on to get a PhD at Stanford in 2016, where she did some pioneering work that actually related to some work that we do here in my research group, using uranium isotopes and other isotope systems to understand changes in ocean oxygenation through time, how oxygen abundances have changed in the oceans through time, and the relationship of that to mass extinctions. So Kim is really interested in reconstructing how ocean chemistry has changed over time and how that relates to the evolution of life on this planet, which is a very vibrant field with lots of interesting things to still discover. From Stanford, she went on to do a postdoc. She got a prize postdoc, the Agaron Geobiology Postdoctoral Fellowship, which is a very competitive thing to try to get. She took that to UC Riverside, working with Tim Lyons there, before she went on to her current position at Penn State University, where she's an assistant professor. She has won some awards of note, actually many awards, a couple to highlight: the Doris M. Curtis Outstanding Woman in Science Award from the GSA, and the GSA's Geobiology and Geomicrobiology Division Pre-Tenure Award. GSA is the Geological Society of America, which is one of the largest professional societies of geoscientists in the world. She also, among other things, was the co-founder of the Asian American and Pacific Islanders in Geosciences organization, which I think she's going to talk about a little bit towards the end of her presentation. So with that, it's great to have you here, Kim, and I'm looking forward to your science talk, as well as learning a bit more about the things you've been doing outside of science that shape who actually does science. So thanks very much.
All right, let me figure out how to share the correct screen. And I think there, hopefully that looks right.
Yep, that looks perfect.
Great, well, thank you so much, Ariel, for the really kind introduction. I'm really sorry it didn't work out for me to be at ASU in person, which I really wanted to do under other circumstances. As he mentioned, a lot of the work that I am going to show today and that I've really been interested in was inspired by a lot of work that was done at ASU and is still being done at ASU. So it is really too bad that I wasn't able to be there in person. So in this talk, I'm going to discuss how we can use mass extinctions in helping us understand the Earth system. And we'll take a look specifically at how oxygen availability in the oceans can change due to extreme and rapid climate change, which has negative effects both on animals and on planetary habitability. So before I jump into the meat of the talk, I want to acknowledge many of my collaborators who I've worked with very closely for the work I will show today, specifically Dalton Hardesty at Michigan State, as well as Dominic Hulsa and Andy Ridgewell. A lot of the talk I'll be showing, a lot of the results I'll be showing was actually led by Dom. So he deserves a lot of credit for the work I'll be discussing. I've also been lucky to be funded by several and supported by several organizations, including the PRF organization, NASA, and the Aragon Institute. So I'm first going to talk about why I care about mass extinctions. And a guiding question in the fields of geobiology, biogeochemistry, and Earth history, sort of the subfields or subdisciplines that I'm in, is how the evolution of the biosphere has profoundly affected the geosphere and vice versa, because there's a lot of interlinking relationships between these two aspects of the Earth system. This is the major motivation that drives my research. To illustrate, I like to show this figure, which is a compilation of the number of marine families, animal families through the Phanerozoic, plus an additional 100 million years. So this is the start of the Cryogenian around 700 million years ago. The Phanerozoic starts here. This timescale has since been updated, but the overall trends are still the same. And then we are at 0 is today. So this compilation shows two major features, which I hope are pretty clear. One is that there's an overall increase in biodiversity through time. And these are punctuated by several large decreases, or what's termed mass extinctions. And the arrows here are pointing out what's called the big 5 mass extinctions, which are simply the ones with the largest impact on the fossil record. And so the focus of my talk will be on how does environmental change occur during periods of extinction, and what are the mechanisms that respond to these changes in the environment during these instances. So I'm going to take a step back and talk about why these mass extinctions are so useful. I view them as critical windows into the underpinnings of the Earth system, and I'll lay out a few examples or arguments as to why they can be really useful for geologists and Earth scientists. So first of all, extinctions represent perturbations to the Earth system, and they're usually related to changes in the climate or the environment. And so they have a lot of utility for understanding future changes to the climate and environment and how the Earth system will respond. And you can see this in this figure here, which is from a review paper, a really nice review paper. And they're showing extinction rate over the last 300 million years until today. And what they highlighted in this review is that the time intervals with really high extinction rates are all corresponding to large volcanic events, which in this case, these are large igneous provinces. The exception is the Cretaceous Paleogene extinction here, which is also coincides famously with a very large impact, although it's still a standing debate what the relationships between impact, the Deccan traps, and Cretaceous extinction truly are. Regardless, what's clearly shown by this compilation is that these geological processes can transiently impact environmental conditions on a global scale, causing really large effects on the biosphere. As someone who cares about the feedbacks and processes that respond to these perturbations, these events can help us understand how these feedbacks actually play out and their consequences on long time scales that can be difficult for us to otherwise understand. So these geologic perturbations can trigger different processes and feedbacks that act on different timescales. And again, these are generally beyond the historical record or the focus of GCMs or global climate models. So just to illustrate, a shorter term effect, which is the cooling of the climate from sulfur aerosols, shown here as a result of volcanic eruptions, is relatively limited. This can be important on decadal to centennial timescales, while others are much longer. So the increase in CO2 from volcanism can result in increased warming, which then stimulates more weathering on continental surfaces. And this serves two important purposes for life. One is that this is a way to draw down CO2 from the atmosphere and thereby returning climate to a more stable state. But this process can also increase the delivery of nutrients to the oceans, which can then fuel photosynthesis and lead to reduction of well-oxygenated areas in the ocean. Just to give you another perspective on this timescale issue, this is another way of viewing the consequences where time is now going from left to right. So pre-extinction, this is meant to represent a taxonomic tree. There's a large diversity of different taxa. During the extinction event, many of these groups terminate, and then there's a slow diversification after the extinction. And so often, the trigger is short-lived, but the consequences are long-lasting. I also included this figure because it demonstrates that the ecosystem post-extinction can be very different from the pre-extinction world, meaning the kinds of organisms that populate the Earth have changed. So another cartoon version of this is shown here, where this is the pre-extinction ocean. Then you can see that there's massive death and die-off during the extinction. And then once the ecosystem has stabilized or recovered, there's an equally large amount of diversity, but the organisms that now populate that ecosystem have changed. So you tend to think of mass extinctions as these horrible depletions of biodiversity, but they are also sources of incredible biodiversity. And this is captured in that Sapkowski curve I showed earlier, where some of these large increases in diversity actually follow some of the most dramatic extinctions. Understanding these feedbacks that I was just talking about are also ultimately important because they are critical for maintaining a habitable world that has supported life in various forms over 3 billion years and complex multicellular life over the last half a billion years. So not only does a habitable planet require certain physical characteristics or parameters, such as the size or distance from its host star, but the regular occurrence or the frequency of these geologic triggers, as well as the presence of the feedbacks, whether they work or not, are important for determining whether life, if it could evolve, could actually persist on a given exoplanet. So on the right, I'm showing an example of how, as a sun solar luminosity increases with age, that can have strong impacts on climate. And depending on whether there's positive or negative feedbacks, that can then determine whether that planet stays habitable. So this is a simple cartoon. I'm just showing two different kinds of negative feedbacks as solar luminosity warms, just to highlight that some of these negative stabilizing feedbacks can be directly related to the presence of life, whereas others can occur on an abiotic planet. So again, some of these might actually be directly related to the presence of a biosphere. The last thing I just want to highlight is that these extinctions represent major shifts in the biosphere that are typically recorded in the fossil record in our Earth history by macroscopic complex life. But without a doubt, these climate perturbations also have really strong effects on microbial biogeochemistry that is not as well preserved in the fossil record, usually only in biomolecules or as geochemical signatures. So the basis of my talk today will actually be less the effect on the macroscopic complex life, but more on the effects of these climate perturbations on the microbial world. In this talk, I'm going to focus on oxygen. And the reason why is because there is a strong relationship between oxygen and some of the major evolutionary trends throughout our Earth's history. So one of the major observations is that as oxygen has increased in the atmosphere, and that's what's shown in this top panel in blue, this is the log scale, and where 100% is the present day level of oxygen. As oxygen levels have increased in the atmosphere from the last 4 billion years ago until today, they correspond with an increase in body size, an increase in the complexity of organisms, and an increase in the complexity of ecosystems. So there's two key major increases. They're known as the Great Oxidation Event, which is this event here, roughly 2.4 billion years ago, and then some later Neoproterozoic or Paleozoic oxidation event, which is less poorly constrained, I would say. If you look at the mean body size of organisms, again, this is on a log scale, you can see that corresponding with these increases in oxygenation is an increase in the maximum body size. And really this is representing an increase in the complexity of organisms. So here we have really simple single-celled organisms to slightly more complex single-celled organisms, and then finally to multicellular life sometime in the late Neoproterozoic into the Phanerozoic. And in addition, we see the rise of things like predation in the Neoproterozoic. So again, it's not just that the size of organisms increase or the complexity, but also the complexity of the biosphere as a whole. Of course, the flip side is also true. So mass extinctions are often accompanied by the deoxygenation in marine environments. And this is particularly true in the Phanerozoic when multicellular life became more dominant. So this is another kind of classic figure showing geologic time from the start of the Phanerozoic, so around 540 million years ago, until today. And all I want you to really see is that the presence of these black bars, which are indicative of the deposition of black shales, which are often thought to be preserved best in low oxygen conditions, correspond to extinctions, which are shown here in these arrows. Now, there's been 2 decades that have passed since this figure was published, so you could fill in some more extinctions and also add more anoxic events as well, but there's no question to the first order there's a strong correlation between anoxia and extinction. Okay, so I should step back and talk about what is anoxia specifically. I should say that there is a bit of a difference between how geologists speak about anoxia versus oceanographers. And that's partly because it's nearly impossible for us to directly measure oxygen in the oceans deep in time, when all we have really is the sedimentary record. If you talk to oceanographers, there's a range of degrees of deoxygenation from the Black Sea, in the modern Black Sea here, which has free hydrogen sulfide or is euxinic, to coastal upwelling zones with low oxygen conditions, but they're still present. So those are often termed hypoxic, and those are what's shown in these blue dots here. So I want to show this figure because even though today's ocean atmosphere system is relatively well oxygenated, there's still plenty of areas in today's oceans that are low in oxygen. So it's also not there, it's also quite complex because this manifestation of oxidation reflects the physical, chemical, and biological processes that inhabit our ocean today. So this makes things a little bit more complicated because there's a lot of spatial variability in oxygen. And it also means that if we're sampling a certain location, we have to make sure we understand the local environment in order to interpret it correctly. So for example, if we were to sample off the coast of Mexico, where there's low oxygen today, we would want to make sure that we're understanding how that local condition is affecting our interpretation of some global state. Proxies have been invaluable in advancing our understanding of the evolution of the redox landscape. So I'm going to go over very quickly some of the different proxies that have been used by geologists through time to reconstruct the levels of oxygen. And this is just a quick sampling. So I already mentioned black shales. These are black because they're organic rich, and organics tend to be better preserved when there's low oxygen. So widespread organic shale, black shale deposition can be indicative of anoxia. There's also things like pyrite framboids, which are really small raspberries of pyrite that form in the water column. And they can only form if there's a significant amount of hydrogen sulfide that's present. So if you find a lot of these really small pyrite framboids, you can interpret the water column of that area might have been high in hydrogen sulfide. There's chemical fossils such as biomarkers that can also be the remnants of bacteria that live under certain conditions. So this one in particular, isorenierotane, is indicative of sulfide in the water column as well. And last, there is a whole suite of geochemical proxies that are inorganic in nature that can be really useful when coupled together. So I'm going to focus on inorganic geochemical proxies in my talk. And the reason why they're useful is that they can track redox conditions at a broad range of spatial scales. Some of them are local, some of them are global. And they can also be analyzed and compared in multiple sedimentary archives. So you can test them out in carbonates versus shales and see if they agree. And if they don't, that tells you something interesting and potentially important. So just to give you a taste of the whole toolkit for PLA redox proxies, I've classified them here very broadly as ones that are global versus ones that are local. When I say local, what I mean is that they are more informative of that basin in which they were deposited or the specific region. So for example, if you were to find black shales in the outcrop, that would tell you that one area was anoxic, but not necessarily tell you anything about an ocean hundreds of kilometers away. Global proxies are often called such because they either are directly related to atmospheric concentrations, oxygen concentrations, which are going to be well mixed, or they have long residence times in the oceans, and so they are also well mixed in the oceans and represent a globally integrated signal of that geochemical cycle. We can also discuss the intricacies here, but I mostly am just trying to show the diversity of proxies. You can also measure these proxies in different kinds of rocks. And so there's been a whole bunch of them that have been developed for shales or siliciclastic fine-grained rocks, where there's a few that have also been developed for carbonates, and some of them can also be interpreted in both. So for a lot of this talk, I will focus on uranium isotopes, which I will term Delta-238 uranium. And that's the one in the white box. But at the very end, I will also discuss some of the other carbonate-based proxies as well. All right, so I'm going to discuss how we can use the end primary mass extinction as a way for understanding climate change in a greenhouse world. So the end primary mass extinction is the interval with the largest decrease in diversity over the Phanerozoic. So it represents a really severe extinction or really severe environmental perturbation, and is unique because it represented a fundamental change in marine ecosystems. So labels here, CM, PZ, MD, represent the switch over of what's been called the Cambrian fauna, the Paleozoic fauna, and the Mesozoic fauna, meaning the oceans prior to the end primary extinction consisted of an ecosystem that looked very different than what was now dominant after the extinction. There was also a really long delay in global Metazoan reef recovery, meaning complex life. All the reefs that can be observed for about 5 million years after the extinction are all microbial reefs. That tells you something about the severity of the extinction. The extinction was also widespread in all regions and all latitudes in the oceans and on land. So we know it was a severely global phenomenon. The culprit for this extinction is generally agreed upon to be the eruption of the Siberian Traps, which is located in modern day Siberia. Estimates place upwards of 30,000 gigatons of carbon being released to the atmosphere at rates slower than we're seeing today. But the eruption of the Siberian Traps was also significant because these basalt flows emplaced into a sedimentary basin that already had a lot of coal and carbonates, meaning that the volcanic activity actually led to volatilization of additional greenhouse gases and other poisonous toxic gases into the atmosphere. So this can be thought of as a general analog for modern climate change, or at least a very dramatic shift in temperature. And there's some evidence for this from Delta018 Records, which is a paleothermometer. This is a Delta018 record that I'm showing on the right from Conodon apatite, so the fossil elements of this eel-like organism. And you can make some assumptions and take the Delta018 of apatite and infer some sea surface temperature in the tropics with that data. So that's what I'm showing here. The scale is pretty hard to see. So just to orient you, right here is the mass extinction horizon. This is the actual Permo-Triassic boundary, which is a little bit offset. And then this is the about 5 million years after the extinction, which is often been termed the recovery interval. So, we can take these actual numbers with a grain of salt, but what they're implying is a large increase in temperature of over 10 degrees Celsius over the extinction horizon, with high temperatures being sustained with some increases and decreases here and there for a really long period of time. And it's quite surprising that high temperatures remained for so long, considering the fact that volcanic dating, geochronology indicates that volcanism did not extend very far into the early Triassic. So what are the consequences of this increased volcanic activity? Well, in short timescales, you would have warming followed by cooling. And then on longer geologic timescales, we would expect to see ocean acidification, long-term global warming, potentially changes in ocean circulation, as well as enhanced continental weathering that can feed more nutrients into the ocean, potentially leading to anoxia. If you need more evidence that this was a really severe time interval, you can look at the evidence for carbon cycle perturbations. So what I'm showing you here is Delta013 records, which reflect changes in the inputs of carbon, as well as changes in the outputs of carbon, which is mostly organic carbon burial or carbonate carbon, through this interval as well. So just to orient you again, here's the Permo-Triassic boundary, and here is the boundary between the early and middle Triassic. And the key features I want you to notice is that there's a large negative Delta013c excursion right at the boundary, which is associated with the increase in volcanism. But that following this increase in volcanism, there are still many negative and positive Delta013c excursions, the largest of the Phanerozoic, until they stabilize completely in the middle Triassic. This corresponds with lots of evidence for delayed biotic recovery as well. And so there's depressed global diversity, really small gastropod body sizes, and again, the absence of complex reefs during this recovery interval. And so there's been a lot of debate, both for these shorter term swings as well as the overall recovery interval, about understanding what the relationship is between environmental perturbation. Was the environment simply just inhospitable for this long, or did the evolutionary recovery, was that slow due to ecological effects? So to answer this question, we'll be looking at uranium isotopes as a proxy for marine redox conditions. As a quick primer for how this proxy works, uranium occurs in two redox states. The oxidized form of uranium 6+ is soluble, whereas the reduced form of uranium 4+ is insoluble. So there's a change in the concentration of uranium depending on how much it's oxidized versus reduced. In addition, the isotope ratio of 238 to 235 also varies depending on whether uranium is present as uranium 6+ or uranium 4+. So these are the two most abundant isotopes of uranium. And what has been observed is that uranium 238 is preferentially partitioned into the reduced uranium 4+ form. Okay, so what does this actually mean for looking at uranium in geologic materials? So this is a compilation of data of Delta-238 uranium. Again, that's a way of reporting the 238-235 uranium ratio. This is a compilation of the Delta-238 uranium ratio, for the different input and output fluxes of uranium into the oceans. So this upper arrow is indicating that rivers constitute nearly all of uranium that's being delivered to the oceans, and their Delta-238 uranium value roughly coincides with the continental crust value. Whereas the different output fluxes of uranium, the Delta-238 uranium value varies depending on whether that sink is depositing uranium 4+, here I'm showing that in gray, versus the oxidized uranium 6+, which here I'm showing in the blue and the green. So there's certainly a lot of variability, but overall what geologists and geochemists have noted is that the reduced forms of uranium 4+, tend to be offset from seawater, which is shown here in this vertical line, by a significant amount. And so there seems to be this partitioning of uranium isotopes depending on whether there's reduction or not. All right, so another perspective of how this actually can influence seawater uranium and therefore our geologic record is that we can consider this as partitioning between reducing sediments, which is where your uranium 4 is being removed, and oxic sediments, such as manganese oxides, some carbonate sediments, which is mostly sequestering at uranium 6+. So most of uranium in the ocean, again, is present as uranium 6+, that's the soluble form. And the residence time of uranium in the modern ocean is about 500,000 years. So that's significantly longer than ocean mixing time. So the concentration and Delta-238 uranium value of seawater is pretty uniform. So if we were to imagine that area of reducing seafloor were to increase, then we would remove more uranium from seawater into those sediments. And as a result, we would also see a removal of 238 uranium into those sediments compared to 235 uranium. So the net effect of this increase in anoxia is that we would expect that the seawater Delta-238 uranium and the seawater uranium concentrations to decrease. Now, one of the keys here is that what we're actually sampling is carbonate sediments, or what we assume to be mostly recording uranium 6+. And so we can think of this more as a more passive recorder. This isn't where the action's happening, where uranium is being reduced, but it's recording simply how this sink or this lever is changing seawater itself. The reason why I'm focusing so much on sediments is that uranium is thought to be primarily reduced in sediments versus in the water column due to thermodynamic limitations. And so it seems to be reflecting changes in the bottom water rather than changes in the water column itself. All right, so if we can trust that we can understand these different processes, we can then quantify the aerial extent of bottom water anoxia given any seawater Delta-238 uranium value. All right, so what does this actually look like for the early Triassic? Again, this is the period after the extinction, which is shown here in yellow, during the 5 million years in which we see depressed biodiversity, the absence of Metazoan reefs, et cetera. So this is now data that's been published by many researchers, including several from ASU. There's been like a really great community effort to test whether or not this proxy can be reproduced in different locations geographically. So here I'm showing you 9 different sections. And there's 2 things I want you to notice. These are all recorded in marine platform carbonates or relatively shallow carbonates. So there's good agreement in the first order that there's this large shift in Delta-238 uranium values across the extinction horizon to lower values. Each location shows this shift. However, you'll also notice that within and between these different sites, there's a lot of noise or scatter. So there's a lot of variability that could be significant if we think about the diagenic factors that lead to these variations. And I'll talk more about that at the end of my talk. Okay, so if we were to think back to the last slides I showed, this shift from to more negative Delta-238 uranium values is most consistent with an increase in bottom water anoxia. And this interpretation is consistent with many other lines of evidence. So it's very parsimonious. So I'm showing you a compilation of other lines of evidence for redox changes through this interval, with blue indicating evidence for oxy conditions and black or gray indicating evidence for reducing conditions. And in all cases, we see that we expect there to be the most reducing conditions or the most anoxia during this early Triassic recovery interval. And so the interpretation that our uranium isotopes are recording an increase in anoxia makes a lot of sense given other lines of evidence that are not necessarily have global implications. So as I said just a few slides ago, the promise is that if we can account for the uncertainty in the noise, uncertainty in the mass balance budgets of uranium, we can then quantitatively model what these changes mean for global anoxia. And this is a difficult exercise because there's a lot we don't know. So I'm going to just show you one way that we can try to account for some of these uncertainties. So here's a snapshot of some of the data we've already looked at. You can ignore panel C for now. Panel A is the inferred temperature record from Delta018 of apatite from conodont elements. B is the Delta-238 uranium record. And here we're just looking at about 2 million years, with the red bar here indicating the extinction horizon. So what we've done here is create a box model, but accounted for uncertainties in the diagenic offset, which is probably what's driving these large changes between samples. Uncertainty in the Delta-238 uranium value of the input or the rivers, as well as the uncertainty with the isotopic offset or the fractionation into anoxic sediments, because that can be also highly variable. And so we ran this many times and found that visually the best fit change in anoxia across this interval is that there's an increase from nearly 0% of the C4 being anoxic prior to the extinction to nearly 30% of the C4 being anoxic. And then with a small decrease into the later on in the early Triassic. So this is this first order trend is large, 50 times increase, but it does not indicate that anoxia was complete, meaning the whole C4 was not anoxic in the aftermath of the extinction. So this is important because this gives us some constraints for understanding what kind of mechanistic models we should be thinking about to explain this rapid increase in anoxia, but not a completely anoxic ocean. Okay, so we're going to now test the different mechanisms that can link the climate changes that we know happened during the end Permian mass extinction with the evidence for anoxia. So at higher temperatures, we know that the solubility of any gases, including oxygen, decreases, but this is unlikely to fully explain the changes that we're seeing. There's been a lot of debate about the effects of oceanographic currents with higher temperatures. And with many researchers arguing that the reduced latitudinal temperature gradient would result in a more sluggish ocean circulation. And that has been called upon to invoke really dramatic decrease in oxygen, even in a deep global ocean. So I'm showing you a result of a global climate model that they ran with the end Permian configuration of paleogeography and climate, where they expected to see deep oceans becoming anoxic, which is counter to what we just saw with the uranium isotope record. With higher temperatures, we would also expect there to be more enhanced continental weathering and therefore greater nutrient delivery. And the estimates for how much weathering increase has varied. A lot of this comes from strontium isotope records, such as this one shown here, where the increases in the strontium isotope ratio is indicative of more enhanced continental weathering. However, some of these increases in weathering up to 3 to 4 to 7 times increase are rather extreme and indicate very prolonged increases in weathering that it's unclear whether or not that's supported by other lines of evidence. So in this talk, we're going to focus on the effects of temperature on microbial metabolic rates, and specifically how this might have affected the biological pump, which is driven by metabolic processes of microbes. The biological pump essentially describes the effects of biological productivity at the surface of the ocean where photosynthesis reigns because of light. And then as that organic matter sinks, excuse me, that can result in remineralization or the transformation of organic components to inorganic components of that exported organic matter within the ocean. That can also release nutrients in the water column. And then finally, the biological pump can ultimately deliver a small fraction of organic carbon to the sediments where it is then buried and removed. And fundamentally, at higher temperatures, higher mineralization rates will result in greater release of nutrients in the shallow water column because there's greater recycling of this exported organic carbon. And this increased release of nutrients can then be fed back to the shallow ocean, supporting greater export production. So in essence, with higher temperatures, you can cause this pump to act more vigorously, and this can have pretty significant effects on oxygen. So to test this, we utilized the C-Genie intermediate complexity model. This was with the boundary conditions set to match Permian Triassic paleogeography. The PCO2 concentrations in the atmosphere were prescribed to match sea surface temperatures that we constructed from oxygen isotopes. And this version of the model also simulates organic carbon reaction in sediments, which are important for producing reasonable bottom water Anoxia results. And unique to this paper is a mechanistic representation of the biological pump, meaning we incorporated the effects of temperature on this remineralization rate of organic matter. We added the sulfurization of organic matter, meaning if there's hydrogen sulfide present, that will affect how reactive that organic matter is. It becomes less reactive. And we also changed the organic matter sinking rate. And the reason for this is because there's evidence for changes in body sizes over the Phanerozoic. This is a compilation of body sizes with the modern shown here and the Permo-Triassic shown here. And you can see that the mean body size is smaller at the Permian Triassic. And this is likely related to the change in, or the fact that this event happened before the evolution of planktonic foraminifera and the significant expansion of diatoms and radiolarians, which represent the sinking skeletal grains that can increase the sinking rate of particles through the water column. All right, so these mechanistic models are imperfect, but they can improve the realistic response of biogeochemical processes to environmental conditions. So I'm going to demonstrate this by comparing what we'll term the static model, meaning the one that is not dependent on temperature, with the more dynamic model. So in this model results, what you're going to see is that the temperature goes from left to right for export production. Here, again, how much is organic matter is being exported from the shallow to the deep ocean, the rain rate of that particular organic matter, the burial rate of particular organic matter, and then related to that, how much hydrogen sulfide is present in the water column, as well as how much of the C4 is anoxic. So these are the different parameters that we're going to consider as a function of temperature, which is again the x-axis, and a function of how much phosphate is present, which is the different contour lines we're seeing here. So essentially, if you move from left to right in these panels, we're just going to focus on temperature for now. What we know from the static model is that organic matter cycling is controlled almost entirely by the nutrient concentration. So it's very sensitive to the nutrient contours, whereas productivity and photic zone hydrogen sulfide is insensitive to temperature. It doesn't change very much. And meanwhile, there's extreme sensitivity of C4 anoxia to increases in temperature. And these diamonds represent the pre-extinction interval, the main extinction interval, or the right before the main extinction, and then the most severe part of the extinction is this third diamond here. And so this version of the model would suggest that over 80% of the C4 became anoxic, whereas there was nearly no hydrogen sulfide that was present in the water column. So we can compare these static results to the mechanistic representation. Again, this is where we have higher temperatures playing a role in this biological pump. At higher temperatures, we see a greater proportion of organic matter that is remineralized in the water column because of this temperature dependent effect. This results in more release of nutrients and therefore a positive feedback of nutrient recycling in the upper ocean. As a result, with higher temperatures, we see an increase in export production to depths by up to a factor of 3 with increasing warming compared to the static version. This leads to increased hydrogen sulfide concentrations in the photic zone, which now becomes very sensitive to temperature. However, the organic matter rain rate does not change accordingly. This is generally comparable to the static approach. But what is different here is that the bottom water anoxia now becomes less severe. And so the reconstruction here is that somewhere between 20 to 30% of the seafloor became anoxic, which is much more aligned with our uranium isotope interpretations. One of the benefits of working with the N-Permian is that it is really extensively studied. So we can actually ground truth these CGNE results by comparing data to model fit spatially. This is really difficult to do before we have sediment cores, such as in the Cenozoic. But there's a lot of data that's been published, and so we can exploit that here. So the first panels that I'm showing here are the concentration of hydrogen sulfide in the water column at depths shallower than 1 kilometer, with the yellower colors indicating really high concentrations of hydrogen sulfide. Again, that's really poisonous to life. So we can think of how this might impact the extinction itself. I know the symbols are probably pretty small, but hopefully you can make them apart. The red circles are positive evidence for anoxia or euxinia. Again, that's free hydrogen sulfide in the water column. The crosses, or what looks like really small points, so here's an example there, that's no evidence for anoxia and euxinia. And the circles, or sorry, the triangles are ambiguous evidence for anoxia, or they represent dynamic redox conditions, somewhere that's in between. It's not stably anoxic, nor is it stably oxic. So overall, the model is able to capture the temporal and spatial trends, where prior to any warming, there is essentially no evidence for anoxia in the geologic record, nor does the model indicate that we would expect that to be found in the locations where we have data. Whereas as we see more and more warming, we see larger areas of the ocean that have these high concentrations of hydrogen sulfide, and they correspond to evidence for that hydrogen sulfide. These next panels are plotting the depth of the maximum hydrogen sulfide, where yellow colors indicate shallower depths where hydrogen sulfide is present. So this snapshot is important for understanding the potential role of sulfidic waters to impact the shallow tropical environments where the majority of marine biota lived. And so clearly what you can see is that this packet of hydrogen sulfide rich water shoals to shallower depths as temperature increases, right? There's more and more yellow as we go from the late Permian into the main extinction horizon. Now, it should be clear that this mechanism has been proposed previously to be related to the extinction itself, but here we can show it has some dramatic impacts at some locations, such as the Eastern Tethys Ocean here, as well as the Eastern Equatorial Panthalostic Ocean here during the main extinction pulse. And last, we can compare the CGNE model results to plot the extent of bottom water anoxia. Here, the percentage represents that are reported here, 0.7, 1.7, and 29.3%, represent seafloor where oxygen is less than 60 micromolar concentration, with the green colors indicating well-oxygenated waters. So pre-extinction, the locations of anoxia are pretty limited spatially, but they increase as temperature increases. And again, this generally matches very well with evidence for or against anoxia on a spatial scale. Importantly, again, the main extinction calculation of anoxia at nearly 30% is aligned with estimates from the uranium isotope model that I showed earlier. I should say that some of the model data fit is imperfect. So for example, here in the Northern Boreal Ocean, there's a mismatch there, but that's likely due to the fact that this model is medium resolution. So shallow areas such as this ocean here are represented by only 2 or 3 vertical layers. So it's not, there are definitely locations where it doesn't fail to be realistic, or it fails to be realistic. All right, so hopefully what I'm showing you is that this temperature effect matches with both the spatial distribution of local redox indicators as well as the uranium isotope interpretation for global redox. And so we're able to come up with a mechanism that makes sense, that matches with a lot of different proxy evidence. This modeling also has implications for a more intense biological pump on the record of Delta013C. So I introduced Delta013C earlier as one of our main tools for understanding perturbations to the carbon cycle. So here we're going to specifically zoom in on the extinction horizon in red, where we can observe that decrease in Delta013C. This has been attributed to an increase in carbon inputs with the 13C depleted signature from mantle-derived carbon, as well as from sedimentary carbon that was volatilized during the emplacement of the Siberian Traps. Because of this temperature-driven increase in microbial respiration, we can also lower this Delta013C of seawater. So this is shown in the depth profile of Delta013C in dissolved inorganic carbon, with an increase in temperature resulting in more and more negative values of Delta013C of that seawater. And so, in other words, what we're actually sampling, while it certainly reflects changes in the inputs of Delta013C, might also reflect this spatial variability in Delta013C as a result of higher temperatures. So this might have implications for estimating the volume and sources of carbon fluxes related to climate warming. So just to summarize, these temperature-induced changes in the biological pump can be mechanistically linked to anoxia. We can use uranium isotopes to evaluate how warming temperatures are linked to the deterioration of the marine environment. And specifically, I hope I've shown you that uranium isotopes can help to propose mechanisms that do not require either extreme nutrient inputs of nearly an order of magnitude increase, or a long-lasting shutdown of thermal halon circulation that would have led to deep ocean anoxia. So we think that our proposed mechanism makes a lot of sense, and it agrees with the proxy data that's available. Ooh, I'm sorry. And last are results of implications for interpreting Delta013C excursions that are related to climate change intervals where there's also expected to be warmer temperatures. And just to illustrate, this end Permian event is definitely unique in terms of the severity of the extinction. That's located right here. But the overall relationship between temperature and nutrient cycling may have also played a role in other volcanism and climate-driven events throughout Earth history. So I'm showing Delta013C record here throughout the Mesozoic, where we can see that there's intervals of Delta013C change, as well as intervals of known anoxia. So these implications might be important for understanding how we can reconstruct climate change as well as biogeochemical cycling. So I'll use my last few minutes to talk a little bit about some of the challenges that come with interpreting these records. So carbonates are great, right? We saw from the uranium isotope record for the Permo-Triassic boundary that across 9 sections, they all record this first order shift in Delta-238 uranium. But we also saw that there was a lot of variability, a lot of scatter, a lot of noise. This is probably due to the fact that carbonates are not always the most reliable recorder of seawater because they can be altered quite readily. So carbonates are really useful because they represent a long-lasting part of the geologic record. Carbonate deposition is shown here in blue. And so you can see that they extend very far into Earth's history, into the Archean. They can also be found in multiple sedimentary basins. You can also sample different locations at a given time interval, which is really useful. However, they are prone to being reset diagenetically. So here's 2 different spatial scales in which we can see that taking place. So these clotted areas are a microbial reef in the middle Triassic. And these areas here are the void space that have now been filled in with different cements. And if you measure the geochemistry of these cements, you'll notice that the geochemical proxies vary a lot because the fluids have changed as they filled in these voids. And this process can also affect carbonates on a landscape scale, with the classic example being the Dolomites, which was a previously calcite or aragonite marine platform that has now completely been dolomitized. So this leads us to always ask this question: are we capturing a record of seawater chemistry? And this was first shown by Steve Romaniello, who is a graduate of your program, where he showed that the Delta-238 uranium of shallow marine carbonates, which is shown in this bottom panel, varies significantly from seawater. And this has also been shown since with other samples and different techniques. So I just want to make a quick plug here about ways we can address this challenge that we face. Researchers who want to use carbonate geochemistry to reconstruct changes in the past. Again, a lot of the classic examples of caution are from the Bahamas. These are drill cores from the Great Bahama Bank. And what you can see is that the Delta013C curve varies significantly between these different sites, and that is not due to changes in seawater Delta013C. These are due to changes in diagenesis. Since that paper has been published, there's been a lot of work using the Great Bahama Bank to test the effects of diagenesis on different geochemical proxies. So we just looked at carbon. There's a lot of oxygen isotope data that's measured. Researchers have also looked at calcium and magnesium isotopes. But what I want to show you here is that they've also measured a lot of polar redox proxies in carbonates. So going back to that Venn diagram, here are different proxies that can be analyzed in carbonates. And what I want you to take away from this is that the blue bar represents what you would expect for primary carbonates that reflect oxidizing seawater. So the blue values would represent what you would expect to see if there was no significant diagenesis. But clearly, many of the samples are deviate from this blue area, indicating that diagenesis can have a really large and important effect. And what I'm proposing with my collaborator Dalton Hardesty is that by combining different proxies, and specifically this multi-proxy approach that many in this department, or sorry, in this school have really advocated for, can help us to tease apart these differences in diagenic situations. So I'm showing here another way of thinking about these redox proxies in carbonates as positioned along this redox ladder, meaning that each of these proxies can represent different sensitivities to oxygen availability. And as a result, they'll also respond differently to different diagenic fluids. So I'm not going to go into any detail here, but I just want to throw this up there to show that we can actually utilize different models, both traditional water rock models as well as diagenic models, and give these models a prescribed geochemical composition of the fluid and of the seawater, and determine the trajectory of geochemical change in carbonates under different diagenic scenarios. And the reason why this is then useful is we can take these predictions and match them to what's observed in the geologic record and see whether or not what we are observing is likely related to a change in seawater, or it could potentially be explained as some sort of diagenic regime. So just to illustrate, I'm going to show some previously published and compiled records of different redox proxies, and then I'll finish up. This top panel is showing the sulfur isotope record. I'm not going to go into any detail really, just to show that there's a shift in Delta34S that was derived from change point analyses at around 2.4 billion years, and then a change in variance or the scatter or the variability in the data at around 250 million years ago. If we look at the compilation of uranium isotope data, there is a statistically significant shift at around 260 million years ago. The iodine calcium record shows significant shifts at around 400 million years ago and around 74 million years ago. And the cerium anomaly, another redox proxy, shows a significant shift at around 280 million years ago. So I'm not going to go into the details here, but my overall takeaway is that based on the models I showed previously, there is no one consistent diagenic process that can explain these overall shifts in all of these records themselves. So unsurprisingly, the most parsimonious explanation for this example is not diagenesis or some change in diagenesis that caused all these shifts, but simply a shift in redox conditions. So again, I'm not arguing that I'm the first person to say that, just to show the power of these models to test these different hypotheses. So to summarize my talk, the N-Permian extinction provides a deep time opportunity for data model comparison, allows us to investigate the mechanistic links between climate change and biogeochemical processes. And I hope I've convinced you why mass extinctions are really useful for understanding these changes in the past, as well as perhaps future changes. Carbonate uranium isotope records have the potential to track primary redox changes with some variability as a result of diagenesis that we think can potentially be untangled with the multi-proxy approach. And last, these local depositional conditions can play important roles for determining uranium isotope signature in carbonate sediments, but that they do so in predictable ways. So I just want to leave you here by saying that developing and testing these proxies in the fossil record, and specifically uranium isotopes, can shed light on the relationship between climate and the marine redox state that ultimately drives changes in environmental conditions, as well as habitability of our planet and other planets. As Ariel mentioned, I wanted to put a little bit of a plug and give some background on an organization, a community that I am a co-founder of. We call ourselves the Asian Americans and Pacific Islanders in Geosciences with the acronym AAPI. And I wanted to show you this compilation of data. This is from the NSF Survey of Earned Doctorates, showing the percentage of AAPI representation of PhD recipients for the last several decades. So this is publicly available data. And I want to show this because NSF does not consider Asian Americans and Pacific Islanders to be underrepresented. And that's because for many of the directorates, the proportion of recipients who are Asian American are quite high. The gray line is the population, is the general population. So the most recent data indicates that Asian Americans are roughly 6.8% of the American population. I should also say that these are citizens or permanent residents. But what you can clearly see is that for the geosciences, which are shown in black, the representation hasn't quite matched the representation that's achieved in other sciences. So just to give a bit of background of what AAPI actually stands for, it's a really broad categorization. It's actually incredibly broad. It represents individuals with ancestry or heritage from East or Southeast Asia, the Indian subcontinent, and Oceania. So a large range of cultures, histories, and experiences in the US. It represents a huge range of these social identities, and they don't always fit within an easily shared narrative, including the largest income gap in the US. So the term originated in the 1960s in solidarity with the Black Power movement and in recognition that more issues unify Asian Americans than divide them. And so even though it's not necessarily a perfect umbrella term, it still is useful for advocating for our community. The term Pacific Island, or the group of Pacific Islanders, was added to the designation in the 1980s, but is now counted separately because, fundamentally they represent a really different culture, but we want our umbrella to be large, and so we include them because there's also a lot of overlap. As a result of this diversity in this umbrella, Asian Americans face distinct recruitment and community building issues. And so like many other issues with DEI nowadays, a one-size approach will not necessarily improve budgeting or belonging and justice, equity, diversity and inclusion for Asian Americans. As I said, there's a lot of diversity with this umbrella. Some of the stereotypes are unique to Asian Americans compared to other groups in the US, such as what's been called the bamboo ceiling or the perpetual foreigner stereotype. And there's also different cultural pressures, such as the model minority stereotype, that can limit exposure to the earth and planetary sciences. So to address some of these issues, I co-founded, along with Dana Barra at Brown and Christine Wai-Chen at Lawrence Livermore, a new community that's very early career-based, and it's very community-driven. I think this 300 people was from over 6 months ago, so it might be more, but we have a large number of people who signed up. There's a very active Slack channel, as well as a community listserv. With NSF's funding, we will be launching a new mentoring program, research internship program, and researcher visit program in January and this winter, which we'll announce at AGU. And we're also really excited to build collaborations with other communities and folks working in this space. And so I'm just gonna leave this email up there. Please email me or email this address for more information. And I'm happy to talk more about what we're trying to do. Thanks very much.
Great, thank you very much for that talk, which I enjoyed the end, and I enjoyed the beginning. I enjoyed all of it. And I have to say, just for people who are not in this field, you're doing something really interesting. You're doing a few really interesting things, but in particular, you did this kind of inversion in your motivation. Usually we're interested in, or we say we're interested in, the history of life for its own sake, and we're trying to understand environment to understand how it affected life. And you kind of flip that, right? By saying, look, by studying mass extinctions and understanding what causes them, we learn about the Earth system and its dynamics. And that's like really important for what we're doing to the planet now and understanding that and protecting our future. So that I really enjoyed that inversion of how you framed the whole thing. So thank you very much. That was great. We have time for maybe a question or two, if anybody has a burning question or two. We have one very bold question in the chat, in the Q&A, from Melissa Walker. Can the data that has been gathered be used to predict the next mass extinction?
Oh, Okay. You know, I'm a scientist, so I would always be a little cautious about that. I think there's a lot of differences about the end Permian compared to the current situation. So the biological pump that we showed is the mechanism is a little bit different. Like I said, the body size is increased, meaning the sinking rates has increased. And so I think we could certainly make predictions, but I think I would always be a little cautious. So with these CGenie models, the benefit of them is that they're lower resolution than global climate models. But what that means is that we're not going to be able to get as great spatial temporal resolution. And so as someone who doesn't do GCMs, I tend to trust the GCM folks in their climate predictions as being more accurate on the timescales that are maybe more relevant for the question that's being asked. But I think certainly looking at these effects can tell us about what might happen on longer timescales, maybe 10 to 100,000 years from now, where there's always going to be less certainty there. So I think I didn't quite answer that question, but I definitely am trying to hedge there.
It's kind of a bold question, maybe a little unfair to ask you, but it was there and it was kind of fun. So there's one last question here that maybe you would want to address, and I know it's late, but let's do this. Tim Demico asked, did the unique paleogeography of Pangaea, right, this massive supercontinent, make the Permo-Triassic the big mass extinction?
Yeah, that's a great question. I certainly think it had an effect in making it really slow, a really significant extinction. I think ultimately there's a difference between a trigger, which is what ultimately leads to that initial pulse of extinction, and what can lead to a really slow response. And some of the other modeling I've done on weathering has indicated that something about this paleogeography, this unique state at the end Permian, at the end of the Paleozoic, made the ocean or the carbon cycle more particularly prone to perturbations. And certainly the paleogeography was part of that.
All right, and we'll have to take that up later at some future date because we are out of time. So thank you again very, very much, Kim, for that. That was a great detailed talk with a lot of really cool stuff in it for us to unpack. And I'm if you can stay on a few minutes after, I'd love to talk to you about it a little bit more. So thanks very much for your attention, everybody, and we'll see you next week.
Thanks, everyone.